We're going to talk about equations next. Um, an equation has to have three things in it. Let me. So I'm going to describe what an equation is rather than giving a definition. Um, so we have to have an equal because of the equation. We have to have a left side. So this is what an equation should have. And it has to have a right side. And that's about it. Well, there's a little more to it. The left side has to make some kind of sense, and the right side has to make some kind of sense. And then we have to have a relation, which is the equal equation. And that's it. That's what an equation is. It has to have three parts. So what is not an equation? So let me give you some examples of non-equations very briefly. So if we just say 1 plus 2 equals, that is not an equation because we are missing a right side. We have a left side and an equal, but not a right side. So that is not an equation. And certainly, if we have x minus 3 times x minus 2, that is not an equation either. There's not even an equal. So that's just an expression. Think of it as in grammatical terms. An equation is a sentence in the sense that we have a noun, a verb, and then the rest of the sentence. A noun, a verb, and the rest of the sentence. So this is just a noun. So this is kind of like saying the dog is hungry. So there's the verb, the rest of the sentence, the dog is the noun. So this is kind of like the dog. The dog what? We have to have a verb. You know, we have to say something about the noun in order for us to have an equation. Okay. Once we have an equation, we can subclassify equations into three categories. An equation that is always true, no matter what the value of the variables are, is called an identity. So this is an example of an identity. There's many, many identities. This is just a simple example. So if x is 5, then we have 5 plus 10 on one side of the equation. On the other side of the equation, we have 15. And sure, 5 plus 10 is 15. But the same is true if x is negative 7, for instance. So negative 7, and then that would be negative 14. Negative 7 plus negative 14. Okay, put that in the back burner. And then think about what this is if x is negative 7. So then we have 3 times negative 7 is negative 21. And negative 7 plus negative 14 is negative 21. So it doesn't matter what value of x you use in this equation, as long, of course, we use the same value for all the times that the x shows up in the equation, this is always going to be true. So when something is true, regardless of the input we're using, we have what is called an identity. So this kind of equation is called identity. Let's contrast this with this equation. This equation, let's put a 5 in this equation. So 2 plus 5 is 10. 2 times 5 is 10. 2 times 5 is 10. 10 plus 2 is 12. 10 plus 1 is 11. And 12 is certainly not equal to 11. So that would be false if we put a 5 for the x. If we put a 6, just to give another example, we would have 2 times 6 is 12 plus 2, 14. 2 times 6 is 12 plus 1, 13. We would have 14 equals 13. And it doesn't matter what number you use for x. You know, twice the number plus 2 is never, ever, ever going to be equal to twice the same number plus 1. Okay? It's never going to happen. Even if we plug in 0, let's see, 2 times 0 is, plus 2 is 2. 2 times 0 plus 1 is 1. 2 is certainly not equal to 1. Or if we use a negative number, somebody could say, wait, What if we use negative 1/2? Okay, because the negative 1/2 will create a 0 in here. Well, but negative 1/2 creates a 1 here. So we're still off. So no matter what value of x we plug in, we will always get something that is not an inequality. So this statement is false. It is kind of like saying the dog is hungry, when in reality, the dog has just eaten and it doesn't want to eat anymore. You put food next to him and the dog doesn't want to eat. It's done. So that statement of the dog is hungry, if the dog just ate and is completely satisfied, is false. So the same thing will happen here, except that instead of dog, we're using, or instead of using, dog, we're using this statement. This is the noun, and then this is the rest of the sentence, and that is the verb. So that statement is false always. When a statement is always false, it isn't like we don't have an equation. We do have an equation. That is very important. We still have an equation, but this equation is called a contradiction. Contradiction. Yeah. Let me just give you another contradiction. Let's say you have something that is even more obvious. 2 equals 3. Yeah, because we want to make sure we understand that this is an equation. So an equation means that it's structurally correct, that it has a structure to it, grammatically. You had a noun, a verb, and the rest of the sentence. So we got 2 is equal to, and then the 3. So it's like if I say, today happens to be Friday, but if I say today is Saturday, then that is false, even though it makes perfect sense as a sentence. Grammatically, it is correct, but it is false. This is false always, no matter what. Yeah, this is always false. So consequently, that is also a contradiction. Okay. Some equations, such as this one, could be false or could be true. It depends on the value of x. If x happens to be 3, then 2 times 3 is 6 plus 1, 7. Then that equation is perfect. It is true. If x is 4, for instance, 2 times 4 is 8 plus 1 is 9. Then that equation will be false. So this does not fail to be an equation, just like this one doesn't fail to be an equation, the 2 equals 3. But this equation could be true or false depending on the value of x. Okay, so when that happens, that for some values of the inputs, the equation is true, and for some other values, all it takes is one value, by the way, of the equation, of the variable, the equation is false, then we have what is called a conditional equation. So we can have a conditional equation. So we have contradiction, conditional, identity. Make sure you know those 3, because we have to be able to identify the different kinds of equations we have. Yep. So if we want to demonstrate that this is a conditional equation, we have to do 2 things. We have to show that there is a value for which, oh, this is the one. I was pointing to the wrong one. If we want to show that this is a conditional equation, we have to do 2 things. We want to show there is at least one value for which this equation is true, and then also give at least one value for which this equation is false. That's it. Don't do more than that, please, because if you solve the equation, you would be given only half of the answer. You also have to give a value for which this is false. So you have to do both. Yeah, so I'm going to repeat that again. In order to convince anybody that this is a conditional equation, we have to provide a value that causes the equation to be a true statement, as well as a value that causes the equation to be false. Only providing a value that causes this to be true is not sufficient to demonstrate that the equation is conditional. All we're doing is solving the equation, which leads to the next concept. What do we mean by solving? So, solving an equation means finding all and every one of the conditions that causes the equation to be true. Now, that is very important. All, when we say all in mathematics, we mean it. I'm just emphasizing here every one of the conditions. Because when we are faced with an equation, we have to tell when it is true and when it is not going to be true. And when we solve, we're implicitly stating that if you plug in any other value, the equation will be false. So that is very important. We always provide every one of the solutions. We don't keep anyone out. Because when we're providing a solution, it is implicit that we are telling whoever is reading our work that any other number we use will not work. It doesn't matter what. If we don't find all the solutions, then we have to state so. We can say something like, well, we found a number, but we don't know if that's all the numbers. So we have to state that. Otherwise, it is assumed that you are providing all the solutions. That is a very important message. Yeah, very, very important. There's a lot of nuances that are assumed in mathematics, and that is one of them. When we provide a solution, we mean all the solutions. We're not missing one, all the solutions. Very, very important. Okay. In the world of equations, there's many equations. There's tons and tons of different equations. So we cannot, it's like in biology, if we were studying animals, well, there's too many of them. We have to at one point or another classify them, and then we have to sub-classify them, and then maybe even classify them even more. If we're talking about animals, you have mammals, and you have fish, and you have insects. And I'm not an expert in biology, so that's probably as far as I can go with my knowledge, if that is even correct. But when you're an expert in animals, you kind of want to specialize in one kind of animal, and then you specialize even farther into more subsets. And the same thing happens with mathematics. The world of equations is too rich. There's too many equations. There's differential equations. There's algebraic equations, and then there's all kinds of equations. So we cannot just say that we're good at all the equations, because most of us are not. Anyway, so let's move on to a simple kind of equation, which is called a linear equation. Linear equation. So we have to define what we mean by a linear equation. A linear equation is the one that could be written in a certain form. So linear equation is the one that is equivalent to the equation ax plus b equal to 0. So if you can rewrite an equation so that it becomes this, then we have a linear equation. Let me write that down. If we can rewrite, I'm going to put rewrite in quotation marks, an equation into ax plus b equal to 0, then we have a linear equation. Yeah. So I say rewrite in quotation marks because that has to do with equivalent. We have to define what equivalent is. See, mathematics is very, very formal. By formal, we mean we have to be very, very specific as of what each one of the terms we're using mean. We have to understand the meaning of every part of a sentence in order to do mathematics well. So what do we mean by equivalent equations? Two equations are equivalent if they have the same solutions, the same set of solutions. So yeah, it goes a little deeper, but let's write it down. Two equations are equivalent if they have exactly the same set of solutions. So that's what we mean by equivalent equations. So as an example, we have the 2x plus 1 equals 7. And I'm going to think, let's put down 63 over x equals 21. There we go. Those two equations are equivalent. Why? Because the only number, and I'm not going to demonstrate that here. I'm just going to state it as a matter of fact, but I should demonstrate it, but that's not the point I want to make. I want to make the point that those two are equivalent. The only number that causes this to be a true statement is 3. 2 times 3 plus 1 will be 7, and that's the only time. No other time will this ever be other than, not other time this will be 7. And the only time we get 21 when we divide 63 by something is when x is 3. It will never, ever, ever, ever happen that 63 divided by a number is 21 unless that number is 3. That's the only time ever, ever, ever that it will happen. Okay, so those two equations, which may not seem like they have much to do with one another. I mean, somebody could say, well, 3 times 7 is 21, but yeah, that was a little bit of coincidental. But really, those equations, they seem different, but they are equivalent. And by the way, if you do operations to the equations, eventually, if you start working out operations on these equations, eventually one will lead to the other and vice versa. Yeah. Now let's talk about I just lost my line of thought for a moment because we were talking about equivalent. Oh yeah, linear equations. Linear equations. So let's go back to the concept of linear equations. Some equations too may not seem linear at first. So let's say we have x times x plus 3 plus 5 equals x times x minus 2 plus 7. I'm just making this up as I'm going right now. And somebody could say, wait, that's not linear because x times x is going to give us an x squared. All right. And the only time we have a linear equation is if we can rewrite the equation, if we can have an equivalent equation that looks like this. A constant times x plus another constant. Well, it may or may not be the same constant. equals 0. That's when we have that's how we recognize a linear equation. If we can transform the equation into this form, then we have a linear equation. If we cannot, then we don't. That's the definition. That's the way we figure this out. Now, let's multiply this through let's distribute the x. So this is equivalent to x squared plus 3x plus 5. And on the right side, we have x squared minus 2x plus 7. And then we can subtract from both sides the x squared. Yep. And then if we subtract from both sides the x squared, then we have 3x plus 5 equal to negative 2x plus 7. And then we can add 2x to both sides of the equation. So we have 5x, and we can subtract 7 from both sides of the equation, minus 2 equal to 0. So there, I only want to show that this is a linear equation. That's all I want to show. I don't want to show how to solve it. I just want to know whether the original equation is a linear equation. And the answer is yes. But some of us may be thinking, wait a minute, but there's an x squared. That has to do with the kinds of things we can do to equations to end up with equivalent equations. Because the x squared is throwing a wrench in this equation, is kind of messing up the equation a little bit. How come we have an x squared, and yet we can label the equation as a linear equation? And the reason is because this is an artificial nonlinear equation. This x squared is artificial. This is like saying add x squared and then subtract x squared. So in reality, the x squared is not there. It's like if somebody gives me $1 million and then 1 minute later they say, oh, by the way, give me the $1 million back. Well, do I have $1 million? In reality, no, I don't. Because if somebody gives it to you and then they take it away, within a minute, there's nothing you cannot spend, and you cannot do anything with it. So that's kind of, can somebody call you millionaire? That's kind of what I'm getting to. No, and likewise, we are just putting the x squared there, but in reality, we don't really have an x squared because we're going to take away anyhow, without any consequences, any major consequences. So, but then that begs the question, what are the things we can do to an equation, and what are the things that we cannot do to an equation so that we end up with an equivalent equation? So let me give you another example. X equals 3. That's a very simple equation. Now I'm shifting gears a little bit. Now I'm talking about equivalent equations. So here we were talking about linear equations and equivalent equations. And here we were talking about equivalent equations. So equivalent. So the point of the example here is to show two equivalent equations. Here, equivalent equations, but also we want to get to the point of linear. So in a way, linear is the important topic of this example. So what I want to show here? I want to go back to the concept of equivalency. Multiply both sides of the equation by 3, rather by x. Multiply by x. So we have x squared equals 3x. I'm gonna use columns because I want to squeeze this in this piece of the paper. We're gonna move this 3x to the other side of the equation. So now we have x squared minus 3x equal to 0. And then we're gonna factor 1x out, x minus 3 equal to 0. And then we're gonna use what is called the zero product property. Boy, this is, let me start all over. It is fruitful to do that. So start with x equals 3, multiply by x on both sides of the equation, x squared equals 3x. Move the 3x to the other side of the equation, x squared minus 3x is equal to 0. And then factor the x. And then we're going to use the property that is called zero product property, which states if the multiplication of two or more things is equal to 0, that means that this could be 0 or this could be 0. So a possibility is that this is 0 or that is 0. And think about that. The only way, absolutely the only way we can get 0 when we're multiplying two things is if at least one of the elements, rather, one of the factors is equal to 0. So we split the equation. Whenever we're using the zero product property, this equation splits. And then we have two solutions. On one hand, x is equal to 0 because either this factor is equal to 0 or that factor is equal to 0. X minus 3 equal to 0. And then we have that x is equal to 3 when we add 3 to both sides of the equation. So initially, it looks like we have two solutions. Two solutions. But we started with this equation, which had only one solution. What is the only thing that causes this to be true? Well, 3. If x equals 3, this is true. If x is not equal to 3, this is not going to be true. This has a single solution. Single solution. So it cannot be that this equation has one solution, but then working out the equation, we end up with two solutions. Something is wrong. Something is messed up. And that's why we need to know what we can do when we are solving an equation, and what we cannot do. Because if we do something like this, a solution will sneak up in our set, a solution that is not supposed to be there. So we have to be very watchful. Remember, solving means finding all and every one of the solutions. Yep. Not more and not less. We have to be very precise, extremely precise. So we cannot give more or less. The thing we cannot do is multiply by the variable. Here is the problem. Multiplying by x caused us to have an extra number that could sneak up. Sometimes it does, sometimes it doesn't. So every time we multiply by a variable, we have to check. So that is the rule, the first rule. Multiplying by a variable may cause extra solutions, so extra false solutions. And notice that I said may. It may or may not, but we always, so every time you multiply by a variable, we have to check our solutions. The same is true if we square both sides. Same is true if we square both sides. And then we also have a consequence of that. Well, if multiplying may add a solution, dividing by a variable may make us lose a solution. So we have to be careful when we divide also. On the other hand, dividing And just as up here, take squaring both sides or taking the square root on both sides in the wrong way may cause us to lose a solution. So on the other hand, dividing in parentheses or square rooting on both sides may cause a loss of solutions. Yeah. Yeah. So we have to be extremely careful when we multiply by variables or divide by variables. Yeah, let's do another example. Just checking what example number we have. So now the next example number in this video is example number 4. This is not a linear equation, but I just want to drive the concept of equivalent equations. Say you have x plus 2. Yeah. This is a little bit of a silly example. X minus 3, I should have multiplied this out, but that's all right. Let's do this. Let's say you have this equation and you want to solve the equation for x. We can multiply both sides of the equation by x minus 3. So x plus 2 times x minus 3 is equal to, well, if we multiply both sides of the equation by x minus 3, we have x minus 3. Yep. And then we can say, well, let's cancel that out. Actually, let's multiply this out and see what happens. X squared minus x, because when we FOIL, we got negative 3x and positive 2x, so we have negative x. Minus 6 is equal to x minus 3. We can subtract an x from both sides of the equation, so we have x squared minus 2x. And then we can add 3 to both sides of the equation. Minus 3 is equal to 0. We can factor this equation into x minus, we have to have minus 3 and x plus 1 for this to work, equal to 0. So we are apparently going from one equation to another equation that is equivalent, to another equation that is equivalent, to another equation that is equivalent, to another equation that is equivalent. And now we have to split that into two equations. The two equations together, I suppose, make it equivalent to that. So we're going to use the zero product property. So that means that either this factor is equal to 0 or that factor is equal to 0. If we solve this equation, x equals 3. And if we solve this equation, x equals negative 1. So again, it appears we have two solutions. You know, if we get lost in the process, eventually we are so happy to get x's, numbers for the x's, that we forget that we have to go back and think, wait a minute, 3 cannot be part of the solution for this equation. Because if we were to plug in 3, we would divide by 0. And we may never, ever divide by 0. Never, ever, ever. So we cannot plug in the 3. So that means that this came out of the process of multiplying both sides of this equation by x minus 3. You know, every time you multiply by the variable, now you may say, well, we didn't multiply by x, we multiplied by x minus 3. For purposes of adding more possible solutions, wrong solutions, it is the same thing. If x is a variable, so is x minus 3. If we don't know the value of x, then we still don't know the value of x minus 3. Yeah. So x minus 3 as a whole is a variable, and we're multiplying by that variable. The x minus 3 is a variable. And so we could have a solution that sneaks up, and it did. It was this one. So we have to reject this solution. And so this is the only one that will work. And again, when we are solving a problem, especially if it's on a test, especially if you have the time, then why wouldn't we check to see if what we found is correct? Yeah, you got the time, and it's a test, so there's points involved. Unless you don't care to have enough points, I suppose that would be a good reason not to check. So, but let's check. So -1 plus 2 would be +1. -1 minus 3 will be -4. So that is that is +1. That is -2. And so is that. And the -2 and the -2 simplify. So we end up with 1 times 1, which is indeed equal to 1. So we're good. And we cannot use we cannot use 3 as a solution. By the way, this is an example of a rational function, a rational equation. A rational equation is an equation where a fraction is involved, where at least there's one variable in one denominator. So that's what we call a rational equation. If there's at least one variable in one denominator, then we have a rational equation. Okay, let's look at more rational equations. Let's start a new page. Example 5. Say we have 1 over x minus 3 plus 1 over x minus 2 equals 1 over x minus 1. And we want to solve this equation for x. Whoa. Okay, this is not an easy problem. Some students start working on problems like this and they tell me, it took me 20 minutes to do this problem. And I'm thinking, you're doing good. If it takes you that long, that means that you're probably doing something right. You know, some students think that a problem should take only a minute. Yeah, if they're easy problems, sure, but this is not an easy problem. Anyway, first, get into the habit of noticing what numbers we may not have as solutions whatsoever. So note that x may not be 1 or 2 or 3. Okay, because if x was 1, this denominator would be 0, and we may never, ever, ever divide by 0. If x is 2, this denominator would be 0, and we may never divide by 0. And if x was 3, this denominator would be 0. So there's 3 numbers that we have to avoid by all means. We may never, ever have 1 or 2 or 3. If they show up, we will do the same thing we do here. We write them down and then we reject them. Simple as that. All right. So, okay. Next, there's a few ways to go about this. Let's combine those two first, although that is not the only way to go about this. There's a bunch of different ways, but let's combine those two. So start with equation 1, with the fraction 1 over x minus 3, and I want to have the same common denominator. So we're going to multiply it by x minus 2 over x minus 2. And then we're going to add 1 over x minus 2, this fraction, but I want to have the same denominator as here. I want to have a common denominator. So we're going to multiply by x minus 3 over x minus 3. And let's leave this guy alone. So what we are doing is rewriting the equation. We're writing a new equation, rather, that is equivalent to this one. We are assuming the solutions are going to be the same. because we're multiplying by 1. And we know nothing is going to be messed up because we already established that we cannot have 1, 2, or 3 as a solution. So that means that this is indeed going to be 1. We're not going to have a situation where we're going to have 0 over 0. That's what we're trying to say. Okay, so this multiplication of fractions will give us x minus 2 times x minus 3 and x minus 2 in the numerator. Then, likewise here, we're going to have x minus 2, x minus 3, and x minus 3 in the numerator. We're going to combine those two now that we have the same denominator. So this will become one fraction, x minus 2, x minus 3. And we have x minus 2 plus x minus 3 of the same denominator. So that means we can simply add the numerators, x plus x, 2x. Negative 2 plus negative 3 plus negative 5, but that is written as minus 5 equals 1 over x minus 1. Okay. One thing, once we have fraction equals a fraction, we can use what is called the cross product. You know, we can multiply those two and make them equal to the multiplication of those two. Now, we may only do that if this is not equal to 0, but we already established that. See, that is the beauty of noticing this right at the beginning. We don't have to worry about that too much once we start working. Just keep it in the back of your mind. Don't lose it, though. Okay, so we're going to do what is called the cross product. So we multiply those two together. 2x, let's write it out first. 2x minus 5 times x minus 1 is equal to 1 times x minus 2 times x minus 3. And then we multiply those two out. So we have first terms, so 2x squared minus 2x minus 5x plus 5 equals x squared minus 5x plus 6. I noticed that the 5x is the same. I mean, we could simplify here, but what is the point of that if I know we can just add 5x to both sides of the equation? And those negative 5x's on both sides of the equation are poof, gonna go away. All right. 1x will go away if we subtract x squared from both sides, because 2x squared minus x squared is gonna be x squared. Minus 2x, keep that 2x. And then the 6, we can subtract 6, rather just 6 from both sides of the equation. 5 minus 6 is negative 1. Whoa. This did not come out the way I anticipated. But that's all right. That's the way it goes. I'm just double checking my steps very quickly. X minus 1. Yep. So 2x squared, negative 2x, negative 5x plus 5. Yep. It looks like we're good. So now we add a quadratic equation. Quadratic equation. Let me review very quickly how to solve a quadratic equation. Yeah, because I wasn't anticipating a quadratic, but that's all right. It's within the things we need to know. So if ax squared plus bx plus c equals 0, and a is not equal to 0, comma, so we cannot have a equal to 0, which is the case in our problem here. A is equal to 1. The coefficient of x squared is 1. And then we have 2, rather negative 2 and negative 1. So that compares to this pretty well. We got 1x squared minus 2x minus 1 equal to 0. And this number, which is 1 is not equal to 0, then, and I hope you know this from intermediate algebra, and if you forgot, just remember it now. X is equal to a big fraction, opposite of whatever b is, plus or minus square root of b squared minus 4 times ac. All of that over 2a. We're going to dig into this in this section of quadratic equations. We're going to get more deep into this. But for now, we do remember this. And if we didn't, let's remember it now from intermediate algebra, the quadratic formula. This is called the quadratic formula, comma, the quadratic formula. All right. In our example, a is the number, the coefficient of x squared would be 1. B is this guy, opposite of 2 or negative 2. And C would be negative 1. Okay, so now let's apply the formula. Okay, so this was a parenthesis. It was just a reminder. And now we can continue. So x is equal to the opposite. This means the opposite because we don't know in advance whether b will be positive or negative. So if b is negative, we have to do positive. If b is positive, then we have to do negative. This minus means the opposite of whatever b is. So b is negative 2. The opposite is 2, plus or minus square root. This is negative 2 squared. Oops, negative 2 squared. So that's going to be 4 minus 4 times AC. So 4 times A times C. 4 times A is 1, rather 4, times negative 1 is negative 4. So we're going to subtract negative 4. All of that over 2 times 1, because A is 1. And the formula calls for 2 times A in the denominator. All right. So this is equal to 2 plus or minus. That is going to be 8, square root of 8 over 2. Now, 8 can be broken up as 4 and 2, and we have to simplify that. Okay, so 8 is 4 times 2. I'm not changing the value of the 8. But then this 4, well, this product under the root splits. So this is 2 plus or minus square root of 4, square root of 2. That is one of the properties of roots. We still have to divide by 2. But all of us know that square root of 4 is 2. So this is 2 plus or minus 2 root 2 over 2. Now be careful when we divide. We have to factor out a 2. 1 plus minus root 2. So factor a 2 from here and factor a 2 from there. Now those two simplify, and we end up with 1 plus or minus the square root of 2. That was much more difficult than what I anticipated, and that's okay, because we should know the quadratic formula anyway. So there are two solutions. I'm going to ask at some point, in some problems, to clearly write down the two solutions. There's actually two solutions here. So on one hand, we have the solution of 1 plus the square root of 2. On the other hand, we have the other solution, 1 minus the square root of 2. So here we have the two solutions. And as I'm boxing this, I'm thinking in the back of my mind, okay? The numbers to be avoided are 1 by itself, 2, and 3. And we don't have one as a solution, as a single solution, just the one by itself. I mean, we have one plus something, that is not just one, or two, or three here, and consequently, we're okay. Yeah, yeah, yeah. So this is an example of a rational equation. Remember, a rational equation is an equation that has at least one variable in at least one fraction, in the denominator rather, of one fraction. Yeah. Oh, solving an equation for something is something important that we have to know. Yeah. Yeah. So solving for something. Yeah, that's a weird title. But this is what I mean. Let me show you an example. Example 6. Let's say you have an equation, A plus B equals C. So we have three unknowns. We don't know the value of A, we don't know the value of B, and we don't know the value of C. All we know is that when you add A and B together, you're always going to get C. Okay. We may write this equation in different ways that are equivalent. So for example, we can put everything on the left side of the equation. So this equation is equivalent to A plus B minus C equal to 0. Okay. Or we can multiply this equation by 3. It's really kind of silly to do that. 3A plus 3B minus C, minus 3C equal to 0. And that's equivalent. Or start back with this equation and add 5 to both sides of the equation. You can rewrite this as A plus B minus C plus 5 equal to 5. There's many ways to write this equation. This is one of the simpler ways, and this is not as simple, but this is simple enough too. Okay. Now, when you have C on the left side and no C on the right side, then we say that this equation has been solved for C. So if we have, by the way, there's a property of equations, the reflexive property. No, I lied, that's not reflexive. Symmetric, sorry. The symmetric property says that if the left side is equal to the right side, then the right side is equal to the left side. In other words, we can just swap those two. Whenever you have an actual equation, we can always swap the two. So C equals A plus B, and that is called the symmetric property of equations, when we can swap the two sides completely. So this equation is equivalent to this one, but it has been solved for C. So this is an equation that is solved for C. How can we tell that that has been solved for C? Because there is a single C all by itself on the left, and there is no C whatsoever on the right. Okay, solve for C because there is a single C on the left and no C on the right. Okay, so this equation has been solved for C. Do we have an equation that has been that can be solved for, or can we change that rather into an equation that is solved for A? And the answer is sure. Okay. We can either start with this equation or we can move on from this equation. I think it's easier to start with this equation. A equals B, rather, A plus B equals C. We can subtract B from both sides of the equation, minus B, and we will have A. So A equals negative B plus C. This equation has been solved. That equation has been solved for A. So this is solved for A. Why? Because there's a single A, nothing else, and there's no A on the other side of the equation. So that equation has been solved for A. This equation has been solved for C. Can we solve for B? Oh, before I move on, somebody could say, wait a minute, could I rewrite it as C minus B? There's a rule in algebra that says the letters that show up in an expression should be written in alphabetical order. There is such a rule. However, for purposes of the classes I teach, I really won't enforce that rule. At least unless I strictly say it in a problem, I won't enforce the rule. So if you write this down, that will be okay. Okay, so this would be okay. This or this, yeah. There is such a rule as we should write things in alphabetical order, but it's a fairly minor. In the big picture, it's a fairly minor thing, and I'm not gonna worry too much. I'm just gonna look the other way if I don't see them in alphabetical order for the most part. Okay. That could change from instructor to instructor. And that's okay. That is the prerogative of the instructor. If we put B on one side of the equation and everything else on the other side of the equation, no B, then we would have solved this equation for B. So B equals, and then we have the same thing. We have negative A plus C, or we may write C minus A. So this would be preferred, I think, in some cases, but actually I don't really care. This is okay too. And so going back to this, is there an equivalent that is not totally correct? I would say sure. If you put B plus A, technically speaking, we should put the A first. But again, I'm okay. So this is the same equation solved for B. Now, the equations that we obtain have to be equivalent to the given equation. We cannot have an equation that is not equivalent. Otherwise, it is incorrect. Then we haven't solved for anything. It would be inaccurate. Now, a question somebody could ask, well, which one is better, this one or this one or this one? It depends on the application. It depends on the application. Yeah, we have a concrete example of that we can use, 7. Okay, the Fahrenheit degrees are related to the Celsius degrees as follows. 9/5 Celsius plus 32. So whatever the Celsius is, if we multiply it by 9/5, add 32 to it, we get the Fahrenheit degrees, the corresponding degrees. And this measures, those are units of temperature. So for instance, 0 degrees Celsius, yeah, so 0 degrees Celsius is, all right, so F would have to be 9/5 times 0. I picked an easy one, plus 32, because multiplying by 0 is going to give us 0. And that's going to be 0 plus 32, which is 32. That's a 3. It looks funny. All right. So, so with this formula, we know that 0 degrees Celsius is the same thing as 32 degrees Fahrenheit. Yeah. He converts Celsius to Fahrenheit. Some people claim that um, about 24 degrees is Celsius is perfect for humans. About 24, excuse me. But I'm going to turn that into an easy problem for me. I'm going to change that into 25, even though 24 is what they say. So 25 degrees Celsius is, well, I'm curious. So 9/5 of 25 plus 32. So we can divide by 5 first. So 25 divided by 5 is 5 times 9 is 5 times 9 is 45 plus 32, 77. So if somebody says it is 25 degrees in Spain, for instance, or in Germany or whatever, uh, well, now you know how much that is. It is 77 degrees Fahrenheit. All right. So when they tell you, if you have a friend somewhere else and they tell you their temperature, such as 25 degrees, oh, that's 77 degrees Fahrenheit, then you can do the conversion. But what if your friend says, hey, what is your temperature over there? And today, I don't know how warm it got today, but let's just say it is somewhere in the neighborhood of 81 degrees. Then how do I make the conversion back to my friend? My friend doesn't know Fahrenheit, only knows Celsius, and we know Fahrenheit, but we don't know Celsius. But now we can change from Celsius to Fahrenheit, but now I need to convert the conversion the other way around. So that's when we need to solve this equation for C. So, okay, I'm going to rewrite this equation here. F equals 9 over 5C plus 32. And now we want to solve for C. So little by little, we have to get the C by itself. All by itself, nothing else but C. Okay. Well, denominators is a little bit of a complication. Denominators are a blessing and a complication. It's both. It's a good thing, but it's a complication too. So we want to live with them, but we want to learn to live with them. But sometimes if we can, let's multiply by 5. I don't want to talk too much about that. Let's multiply by 5 the whole equation. So we end up with 5F equals 9C plus, well, 5 times 2 is 10, and 5 times 3 is 15. Well, 5 times 30 is 150, plus the 10 we have is 160. Is that right? 32 times 5 is 150. I believe that is right. 5 times 2 is 10. We carry 1. 5 times 3 is 15 and 116. So yeah, 160. So what we can do is, again, we want to leave this C by itself. So first I get rid of the fraction. Then I'm going to move this guy to the other side of the equation. So 5F minus 160, I'm going to subtract 160 from both sides of the equation, equals 9C. And then we can divide by 9 on both sides of the equation. Boy, that looks wrong. So 5F minus 160 over 9 is equal to C. Let me pause for just 1 second. I'm back. Yep, it is correct. It just looks funny the way I solved that. There's another way to solve it, which I'm going to show in a moment, but it does look a little weird. So there's C. Now, by the symmetric property of equations, we can put this C on the left and just rewrite this as 5F minus 160 over 9. All right, so let's say as an example, sub-example of this example, it is 81 degrees here where we are. And so C would be 5 times 81 minus 160. And after that, we have to divide by 9. So 400 and 5 minus 160. And then we have to divide by 9. So 40 minus 16 is 24. And then we divide by 9. And then it gets a little tricky because that is not completely divisible by 9. So we can do 2, 4, 5, divide by 9. So we end up with 2. And I'm going to do the subtraction in my head. 2 times 9 is 18. So we have 6 left over. 7 times 9 is 63. So there's 2 left over. So we have 27 degrees and 2 9s. So if you want to tell your friend how warm it is in here, and it happens to be 81 degrees, then you can say, well, I'm gonna make the conversion for you. It is just a little more than 27 degrees. It's, if you round it to the nearest degree, it's going to be about 27, just a little over 27 degrees. Yep. One more example, very quickly. This example is a little interesting, handy. 1 over x plus 1 over y equals 1. We want to solve this equation for x. So that means that we have to have x by itself on one side of the equation and nothing else. There's many ways to go about this. Some people want to subtract the 1 over y, which is not necessarily wrong. Yeah, let's do that just to show how things could happen. So 1 over x equals 1 minus 1 over y. Now, this is not it. That's not the answer, because the x is not by itself just plain x. It's 1 over x, not x by itself. So this is not being solved for x. And somebody could say, well, can we flip this and just flip the other side? And the answer is yes, but there's going to be a thing. We have to flip the entire thing, 1 over 1 minus 1 over y. And this solution is not simple enough. When we provide solutions, we have to have them in the simplest, most simple form. We lose points if we don't write the answers as simple as possible. That's a universal rule in mathematics. Whenever we provide an answer, it has to be as simple as possible. And the reason why this is not simple enough for us is because we have a fraction within a fraction. So this is a compound fraction, and that adds complexity to the answer. So a fraction within a fraction is a compounded fraction, and we want to avoid that. So we got to do some work. One, if I want to have a common denominator, is the same thing as y over y. All right, so we're going to combine those two. Now that we have the same denominator, this is 1 over the fraction, which has y as the denominator and y minus 1 as the numerator. All right, now when we divide by a fraction, we're really multiplying by the reciprocal, y over y minus 1. So there, x equals y over y minus 1 is this equation solved for x. If you ask for the solution of the equation solved for y, so first let me write this down. So this is solved for x, y, how can you tell? X is by itself on one side of the equation, completely alone, completely by itself, nothing else. It's not 1 over x or x squared, nothing, just x. It's not the absolute value of x. It's simply x. On the right side of the equation, there is no x whatsoever. That's how we can tell. Okay, now notice that this equation is symmetric in terms of x and y. What I mean by that is, if you replace the x and the y, we still end up with the same relationship. The reciprocal of x plus the reciprocal of y is 1. That's what this equation is saying. This is completely symmetric with respect to x and y. That means then that if we already have one answer, and that only happens if we have symmetry, otherwise, no, we may not do this. The solution is going to be pretty much the same if we solve for y. Isn't that interesting? But that only happens if we have symmetry within the equation. Otherwise, we cannot do that. So that is the same equation solved for y. All right, we're going to stop this video here.